talvez possa começar. So I'm going to speak Portuguese, so you don't.
Sure, go ahead.
You don't hear me botching your CV or botching in Portuguese.
You can lie as much as you want.
Okay. Tá ligado? Alô? Então, a gente, quer dizer, o Koby Rubinstein é do Technion em Israel e ele está visitando aqui por causa do Flávio Greenspan, que contactou o Fábio Com, que me contactou, e a gente está super feliz dele ter podido dar essa palestra. Ele fez tanta coisa que eu não vou descrever tudo, mas ele fez doutorado no Quran. Nelson, I went to Quran. Anybody else? Alguém mais daqui foi estudando Quran? Anyway, there were at least 2 people who went to Quran here. E ele foi pró-reitor de pesquisa do Technion, Research.
VP for Research.
Bom, ele estudou tudo. E trabalhou com todas as outras coisas também, com partial differential equation, hydrodynamics, superconductivity, conductivity, optics, physiology, medicine, psychology, nursing. Mentira, esses últimos eu acabei de inventar. Bom.
Okay, I'll go from here. Okay, thank you very much. I must say this presentation was prepared for engineers, not for mathematicians. The good news, it should be easily understood by this audience, but at some point I'll add a little bit of mathematics, because at some point there is deep mathematics that I'm hiding from the engineers, but I won't hide it from this audience. So I'm going to talk about two main subjects, both relate to visual optics. The first one is how to design premium spectacles. What do you mean by premium spectacles? People above the age of 45 need correction to far vision as all their life, but also for near vision, because the eye lens contract less than before. And then we use so-called multifocal spectacles or progressive addition spectacles, where when you look forward, in the forward direction, you get far vision. More toward the nose, you get near vision, and you must have a smooth transition between the far vision and the near vision. Almost anybody who has spectacles over 45 years old now is using some kind of multifocal spectacles. As you see, the design of high quality. Yeah.
So for this audience, this is purely research interest, because nobody here is over 45.
Sure. I don't assume any prior knowledge of mathematics or visual optics or anything. As you'll see, the design of multifocal spectacles requires very high-level mathematics. It's a very surprising fact. When I first realized it, I was really amazed. But right now, you cannot find on the market any company selling multifocal spectacles of high quality that does not imply mathematicians. You cannot do it without high-level mathematics. The second subject, starburst. When you look at night at a very far object like a star or a street light, you see sometimes rays coming out of it. This is called starburst. The second part of the talk, I discuss why you see them, why they occur, what is the reason behind them. Now the mathematics is simpler, but still very interesting. Using some not too difficult mathematics, we were able to explain what people observe and why do they observe them. Okay. Oops, no, what happened now? What did I do now? I did something wrong, I don't know what. How do I go down? Page down? Page up? Okay.
Baseball.
This is to go down?
Yeah.
Okay, fine. Okay, well, I got it. So something about the history of spectacles. Seneca the Younger, the philosopher from the Roman Empire, already observed that if you look at an object through a piece of glass or water, they seem larger. Quite interesting that this method is now back into practice for designing so-called adjustable spectacles for third world countries, but this will be out of my talk today. Bacon was the first to actually start talking about spectacles. You can see here a statement from Bacon's writing. Now, if you look at some craftwork from the 12th and 11th centuries, it's clear that you use some kind of magnifying object. However, the big step forward in optical design was the invention of frames. This is something nobody, until the 15th century, nobody had the idea of a frame to hold the lenses in front of the eyes. We use spectacles, which is a plastic, non-organic object, but this creature also uses, it features as eyes with a lens consisting of some mineral. You're not the first people to use, the first animals to use minerals to get better vision. Oh, now what happened? This? Okay, this is here, okay? Now, people could not do real design because they didn't know how rays are refracted. Ray refraction, Snell's law, that many of you learned in high school, this was only discovered in 1621 by Snell. Optical design was for many, many years occupied with designing microscope or telescope or cameras, other other optical devices. But the entire theory of aberrations of optical design has not been, does not have an impact on spectacle design. You'll see as I go along why this is so. One reason is the eye is not not a symmetrical optical object. We have some direction in our vision called cylinder by optometrists. I'll explain what it is later on. Another reason is when in a microscope you always look for the forward direction, but the eye keeps moving. And the eye scans the lens, the spectacle lens, in many, many directions. Therefore, it's an asymmetric design by definition, and this causes, as you'll see later on, great difficulties in design. People still design something, but couldn't solve the problem of multifocal spectacles. Okay, so the key object is the ray. So the ray was known already to the ancient Greeks. They knew what are rays, and they knew how rays are reflected, the reflection law, and they knew that they are refracted by water, but they could not find the law of refraction, how a ray is refracted when it goes between one medium to another medium. This was discovered only by Snell in 1621. However, recall that a ray is not a physical object, it's a mathematical object. There's no single ray, there's only a system of rays. And therefore, we often talk about wavefront, but before this is Snell's law. That I believe many of you saw it already in high school physics class. A ray coming from a medium refraction index n, let's say air, it's refracted by here a flat surface, into another medium with refraction index n prime, say water. The angle of incidence is I prime is the refracted angle. This is Snell's law. Snell's law said that the incoming ray, the outgoing ray, and the normal to the surface of reflection are coplanar. And this is a very simple geometric or trigonometric law that now discovered. This was the foundation of modern optics or geometrical optics. However, as I said, rays are not a good physical object to work with. You should work with wavefront. Wavefront is a physical object. And what is a wavefront? Well, there are a system of rays, and the wavefront are surfaces that are everywhere normal to the rays. So we can talk about either about rays propagating in space or about wavefront propagating in space. It can go between one and the other easily. My point is going to be that the wavefront contains the information about the focusing of the optical system. So we should really work with wavefront and not with individual rays. However, the refraction law by Snell is for rays. If I want to follow wavefront, I have to design a new refraction law for the entire wavefront, for system of rays. This will be a major point, as I point out later on. Okay, now here I explain to engineers what is differential geometry. So I do it very quickly here because I'm sure you all know that. So what are curvature in surface? So if I refer to a spherical shape, then it converges to a point. Great, focal point. Now in general, if you have a surface, take a point on the surface, and you draw all curves passing through this point. And then for each of them, you look at the largest and smallest radius of curvature, and you can define the principal curvature of the surface at any given point. These are principal curvatures, and a point where kappa 1 is the same as kappa 2 is called umbilic point. That's more or less like a locally spherical shape for the wavefront. They're called umbilic point. But in general, points on the surface are not umbilic. And the difference, kappa 1 minus kappa 2, with absolute value, is what ophthalmologists and optometrists call cylinder. Now, here I want to add something. When you go to the optometrist, you get a prescription. What do they give you? Well, they give you three numbers. Number they call S, a number they call C, and the number which is some kind of angle, alpha. The optometrist gives you a prescription with three numbers. Sphere, this is called sphere, this is called cylinder, this is called angle of cylinder. This is a terrible way to write down a 2x2 symmetric matrix. What they really give you in the prescription is a 2x2 symmetric matrix. Let's say A11, A12, A12, A22, where S is the average of the two eigenvalues. C is the difference between the two eigenvalues, and alpha is the angle of the largest eigenvector with the x-axis. So optometrist really gives you 2x2 symmetric matrix in disguised by these three numbers. Okay, so this C tells you that if you have cylinder in your prescription, if C is non-zero, that for almost everybody is some cylinder, then this means that to focus light into his eye, somehow the wavefront going to the eye must have two different principal curvature at any point. This is the meaning of cylinder in the prescription. But recall the fact that a prescription is a 2x2 symmetric matrix. Why they do it in this way, not in this way? Historical mistake. But they keep doing it. So, the only country in the world they try to change it is South Africa, and they failed. So optometrists everywhere in the world still use this very strange system of writing down 2x2 symmetric matrices. They have no idea that what they write down is 2x2 symmetric matrix. They're used to only to this notation. Okay. So this is the key picture of how to design a lens. So the world consists of many, many point objects. Each point object emits a spherical front. This is a spherical front. Think about you dropping a stone in a lake. You see the wave propagating in a spherical shape. Then this little wavefront hits the lens, and it's refracted by the lens. You don't see it inside. Again, refracted by the inner part of the lens, go to another medium, and then propagate toward the eye. And this happens to many, many objects outside. To design a good lens, you need to represent the world by thousands of objects. Some of them will be far in the upper part of the spectacle. Some will be nearer to the eye in the lower part. We need to see a good focusing for near vision. Okay, now we need only to follow a small piece of the wavefront because the pupil is relatively small. That's enough. So for any, in fact, what happens, if I write down the wavefront, let's call it a G. I write it down, it's a function near the center of the pupil, then there are linear terms come which are irrelevant for vision, then come the quadratic term in a Taylor expansion of the wavefront. This is the form, the A11x squared plus 2a12xy plus a22y squared plus higher order terms which are not important for spectacle design because the pupil is so small. So only this term come into effect, and this is the local shape of the waveform. Okay. Now, the eye is an autofocused optical element, and the eye lens, it contracts or relaxes to obtain focal distances, depending on the object you look at. However, we start losing this ability about the age of 45. It degrades more and more and more, and everybody here who is over 45 years old knows quite well. So if you never needed far vision help, you can use reading glasses, okay, with increasing number. If you did, you need something else. You need to correct for far vision and for near vision. It's getting worse and worse as we get older. However, here's another issue. When we look at a nearby object, the eye goes toward the nose. This is the point. This is called convergence. It's an instinct. Don't control it. So try to see for yourself. Look at a nearby object, and the eye goes down toward the nose. So the whole idea here, is to use the fact that we lost dynamical ability in contraction of the eye lens with the still remaining ability of the convergence. And this is why we say, okay, and then if we look at a nearby object, the eye will naturally go down toward the nose. Let's put here an area for near vision. And far, when I look forward, let's put a spectacle correction for far vision. So the first one to do it was Benjamin Franklin from the US. He designed what we call bifocal spectacles. So there's a line here. There are two lenses fused together. You can see a line. This solution has two drawbacks. First, some people have hard time to adjust a very sharp change in the optical power. Second, cosmetic. A spectacle is a cosmetic object. Put it on your face. People look at you, they see you with spectacles. And some people don't like the line here because they look older. If you have a line in bifocal lens, it means you're over 45 or 50 or 80 or 90. People like to look young. So they didn't like this line in the bifocal lenses. And if you have a smooth surface like what I have here, people don't know my age unless they see my receding hair. So that's why people try to design spectacles that will smoothly go from far vision to near vision. As you'll see in a second, mathematically, it is impossible to have a perfect touch lens for a very deep reason. Okay, so this is the design goal. Because the eye keeps moving around. We call it it's a cosmetic element. It must be thin. Nobody would buy a lens this thick, right? Now the trouble is that the goal of having varying optical power and excellent vision is in conflict. And the deep reason behind it is a mathematical theorem from differential geometry. It says the following thing. Suppose you want a surface where on the one hand, every point will be umbilic. So kappa 1 is principal curvature are the same for every point, and the optical power and the mean curvature will change from point to point, because the mean curvature in the lens, more or less in the roughly way, the mean curvature determines the focusing. So you want, say, mean curvature H1 here, mean curvature H2 here, and smooth change is the mean curvature. But the only surface that is umbilic everywhere is a sphere. And then the mean curvature is constant. So this mathematical theorem that the only surface that is ever umbilic is a sphere is the reason for a multi-billion-dollar industry of premium multifocal spectacles. You can't have both. So you must somehow optimize. Okay. Now, people tried for many years to design multifocal spectacles, but the first successful design were by Martinaz from France and Canot US. Martinaz really gave this patent to Essilor. They're still now the largest manufacturer multifocal spectacles in the world. But they didn't design. Basically, they tailor the surface for many of hyperbolas and parabolas. They're not a design in the optical sense of the word. So here is our design methodology. As I said before, many point object, each one is emitting a wavefront, going to the lens, refracted several times. So what we do is there's a step that I am jumping for the engineer to explain it to you now. Suppose this is the front surface of the lens, and there is a spherical wavefront coming from the point object hitting it. It's being refracted by it. Now, Snell's told you how to refract a single ray. That was Snell's law. But I'm not talking about a small piece of a wavefront. See, the ray is in the linear terms. I didn't write down. Let's say B1x plus B2y. This comes with the normal to the surface. This is the ray. So a key tool that we developed was an extension of Snell's law. How to refract not just a ray, but an entire piece of a wavefront. I won't write it down. It's a very complicated law, how to write it down, but it's a self-contained law. One formula for kind of a meta, or I call it quadratic refraction formula. How to refract an entire piece of a wavefront in the surface. So in this way, we refract the wavefront here, refract it again here, and try to achieve it after refraction, the shape that fits the prescription. Okay. Okay, so this is what I explained. That's what we did. This is our formula. However, we were very happy. By we, I mean my colleague Gershon Molansky and myself that developed this idea. And in fact, we have a small company that developed the software and sold it to a manufacturer of spectacle lenses. So we were very happy when we discovered this formula for how to refract a small piece of a wavefront, not just a single ray, kind of meta Snell law. But then one day I looked for some strange reason into Maxwell's collected papers, and I saw in a forgotten paper by Maxwell, 19th century, he wrote down our formula as well. So this is formula really due to Maxwell, although I rediscovered it. So okay. So refract the wavefront twice, once here and once here. And since I know the wavefront shape, or I take some shape, a trial shape, I can find out the refraction law, so the principal curvature of the surface. What you see here at the h of p is the mean curvature of the refracted wavefront after refraction by the two lens surfaces, once here and once here. And A is the difference between the principal curvature. And as I said, it's impossible to have a lens that will have, suppose the person has no prescription and no astigmatism in the prescription. So the cylinder is zero. Then I want A to be zero everywhere, but this is impossible. As I said before, there is no surface that has varying mean curvature and is oblique everywhere. It's possible to do it. In fact, you can even quantify it. Here is the theorem. Suppose the center line was oblique. Every point here was oblique. Well, this I can do. Now, the mean curvature varies from top to bottom. And this theorem tells you that if the mean curvature varies, then the change, the astigmatism will grow in the horizontal direction, twice as fast as the variation of the mean curvature. This can be seen in actual design, this mathematical result. So when you cannot do something exactly, you optimize. That's okay, you can optimize. So I choose, this is the function to be optimized. F and G are the two lens surfaces. And H di is what I want to achieve for the wavefront after refraction. This is the unpleasant astigmatism. It's there. I can't avoid it. AI and BI are weights that the designer can use. These are very, very important because you want to design different kind of spectacles depending on what the market wants. Some people want narrow frame, wider frame, longer spectacles, then the designer can play with the weight, what's important, what's less important, higher points on the surface, and you optimize this function. Now, easy to say, hard to do. Because this is a just mathematical expression. You try to optimize it, you realize there is deep mathematics behind it. Because if, for example, if I express all the curvatures by the lens surfaces, I obtain fourth order nonlinear PDEs. Not a pleasant object to work with. Nevertheless, that's what you have to do. That's what you have to do. It's a difficult optimization problem. It requires thousands of points. I don't know if anybody here is doing numerical analysis. If you are here, you have to design either finite elements, an element heavy enough for fourth order PDE, or some other method. Or another method. We use different type of optimization codes for this. Okay, now, first of all, you need thousands of points, so it's a very heavy optimization problem. Cosmetic issue, lens must be thin, otherwise nobody would buy it. How to choose the weights? It's part arts, part engineering. I want propose to use AI before AI became popular word. I don't know if to use it because I stopped working on it about 10 years ago. I don't know if to use AI and for choosing the weight now. Here is an example. This is an example of a lens where the change between far vision and near vision is 2 diopters. So here, this is the far vision. The blue part is the good part. Blue part means very little distortion. As you go more and more red, you get more distortion in the visual field. So this lens, this is far vision, this is the near vision for reading. On the side, you see growth in the unwanted cylinder, which is the bad distortion. If with a lens like this, you have a hard time going down the stairs. Because if you go down the stairs, they will be distorted on the side. Okay? This is a commercial lens, because of the competition, of course, the commercial lens. This is a similar requirement in the design by our code. See, no red part, no big, some distortion on the side. That's like the theorem I mentioned before. You cannot avoid it, but much better than this one. And in fact, you can do even better than this picture now. So this is how good you can be with the design. So to do all this stuff, we develop what we call mathematical engine. These are codes to do very, very fast optimization, because the designer hates to sit there at 50 minutes for any design, for any spectacle, but it's very, very fast. I'm not going to any commercial here, but you can find such spectacles here in Sao Paulo if you want. Now they're used by 2 major manufacturers, and production is also a very important factor, but not part of my field. Okay, so this is the first part of my talk. So the design of spectacle, or these multifocal spectacles, is a deeply mathematical object. Second part will be on starburst. So if you ask an American, what is starburst, this horrible candy, don't try it. It will kill your teeth. It's a candy. But for us, starburst is this. When you look at a star or an object like a street lamp at night, then you see rays coming out of it. Okay, these are called starbursts. Now, why do they occur? Why do we see starbursts? So I must start with explaining what is caustic. This is a very quick course on caustics. So there are singularity in the ray field. So look at this image. Each point in the bottom line here is mapped through a line to a point in the top line. These are just a system of rays, but you can see these curves of very high intensity. These are singularities in the ray field. They are called caustics in optics. Yeah. So how to find them? Well, there is the initial location of the ray and the final location of the ray. So there's a ray mapping. The place with the Jacobian of the ray mapping is 0. These are the caustic points. I'm not going to explain why. It's part of an optics course. So mathematically speaking, there is a phase or a wavefront, And this is the mapping defined by the wavefront psi. And this mapping, the Jacobian of it, might have zeros. And these zeros are the focus of the optical system. So basically, focus or caustics are a highly geometrical object. Well known to the Greek, caustic comes from the Greek word for fire, phogo, right? Yeah. Okay, this is a simple example. Suppose this is the initial phase or wavefront shape. You can compute from it the wave mapping, and see, in this case, this is the caustic over here. The focal point of the optical system is, of course, a caustic, the degenerate caustic. Now, caustics singularities are part of geometrical optics. If you write down the full optics or full Maxwell equation, you can find that the fine structure near the caustics, and caustics are singularities, but there is a fine structure around them. This is an example. Look near the fold caustic, you see there's some function. K is the wave number, so K gets very large. This goes to infinity. And this is the area function, which has some internal structure, K to the 2/3. So you can see some internal structure. I'll come to it toward the end of my presentation. But what's really important for us is that we can, once we have the wave mapping, we can compute the caustics. Can compute them. You see in a second, it's a very easy computation. This is an example of caustic that I like very much. What you're going to see here is the following thing. There is a cave. It's a cave, and there is a hole in the ceiling. And the sunlight comes through the hole, okay? And then in the bottom, there is a pool with water. And the water has ripples. And what you see here, the reflection of the ripples in the pool on the cave ceiling. And you see it changes because the water oscillates. See the shape? The people screaming in the cave, you see in the background. And this is me, and this is the water in the pool at the bottom of the pit. It's an example of caustic. And the reason why I like this picture, because the name of the Ein Koby. Ein means a fountain. Koby is me, so I like very much the place itself. It's not far from Jerusalem. Okay, so starbursts were observed already by this fellow Donders. As the ophthalmologist knows the name, he's the father of modern ophthalmology. And he said, many years ago, he claimed that these starbursts are, it is not to be wondered if these stars appear different to different people because of their eye structure. Different people see starbursts differently. You see, I'll show you some examples in a second. So he claimed that it has to do with irregular astigmatism. In the modern sense, we call it high order aberration. It really means not staying in the second power, like in prescription, but going to higher order tegmental or expansion of the wavefront that focuses into the retina. These are called higher order aberrations. So this is the group I worked with. This trio is from Indiana University Optometry School. They do, see in a second, they did experiment in the clinic. People came to the clinic, look at a nearby object and draw what you see. And Norberto Lopez from Spain, he can build actually such systems in his lab. These are my colleagues. So people who came to Indiana School of Optometry must look at a far point object and write down what they see. The pupil was dilated to mimic night vision condition, and they wrote down what they saw on the same template. Sometimes they put artificial lenses before of the eyes to see some other effects. Some people who went to the clinic underwent refractive surgery. So the cornea was shaped to throw away the glasses. I don't know how many people here did the surgery, classic surgery. Some of the people who came to, you see some pictures, were LASIK patients before. And then an album of images was created. So this is a dilation, same scale. Okay. So for example, this person reports different, this person is drawing. So for example, if you put an artificial lens to create -2 diopter bad vision, this crazy shape. Otherwise, you see rays coming out of the origin or other type of images. Here are some other examples. Another person, again, you see points, sometimes strange curves coming out of the origin. There's another guy. Now look at this fellow, or actually this lady. What's the difference? You see much, much larger rays, right? Why? What's special about her? LASIK. She had this surgery to shape the cornea, to remove glasses. And when you do this surgery, you often create high-order aberrations. Okay, terms larger, or in this case, fourth-order terminal antenna expansion. And therefore, at night, this high-order aberration create problems. Less clear vision at night conditions. And you see it very clear. If you look at the album, I can tell by the starburst whether the person did or did not go through elastic surgery. Okay, but still, the question is why these things occur? How to quantify them mathematically or characterize them mathematically? Here are some observations. Very often, the starburst take the shape of rays passing through the origin. Sometimes they radiate from the origin. Refractive surgery is associated with large starburst. If they put the focus, you sometimes you see strange shape. Anybody here wears spectacles. Look at night, today, evening, remove them, look at the far street lamp. You see beautiful pattern because if you now you don't have correction to your vision. Some other effects, I won't talk about them. Because the hypothesis that we had is that they are a consequence of high-order terminal antenna expansion, high-order aberration. It means aberration of vision that are not part of your prescription. No optometrist can tell you what are the high-order aberrations. In fact, it's very hard to measure them. Another topic for another talk. So here is what it means. Suppose you have a perfect eye, then the wavefront, after going through the eye optical elements, is spherical. It focuses at the point on the retina. That's perfect vision. But it doesn't happen, never happens. What really happens is that after passing through the eye optical element, this is an approximation for the spherical part. That's a correction. So psi is a deviation from the standard, from the spherical part. So psi, even if you have perfect vision, even for the optometrist, your prescription is 0. Then this term will be there, but you're also going to have some correction. This correction mathematically comes into the third, fourth, fifth order terminal antenna expansion of the waveform. The quadratic part is here. Here are the high order terms. The third order terms are called comma in optometry. Fourth order are called spherical aberrations. Fifth order, I don't know if anybody who has them. They're very, very, very rare. Now, most of you don't have high order aberration, but you have them, but they are too small to affect your vision. After people with some disease have third order aberrations, large, and people who did plastic surgery sometimes have fourth order aberration because of the surgery. Okay. So we assume that the starbursts are the intersection of the caustic surface of the light with the retina. That's a hypothesis. Let's see if it is in agreement with the observation from the clinic. So here is what we do. First we choose the plane, which is Z0, but after the eye cornea and the eye lens, that is Z0, and X, Y is coordinate in this plane, and it is mapped by the phase into the retina. X prime and Y prime are points on the retina. This is the mapping, P is the phase, and you ask yourself, where are the caustic surfaces? Where is the Jacobian of this mapping 0? If you write down the equation for the Jacobian of this mapping to be 0, not surprisingly for us, this is what you get is an equation for, this is not a PDE, I know phi. This is a geometric equation. The solutions are curves. This is the function of x and y. The solutions are curves. So this curve, the solution to this equation, will give you the curves on the plane v equals 0. Then you can map them into curves on the retina, on the plane x prime, y prime. Okay, when you map them, you get a very simple expression for the shape. So this is an equation for the shape, for the curves on the, oops, so it should be xy here, sorry. For the curve on the initial plane, and this is how they are mapped into the cornea. So remember, this is not a PDE, it's a geometric equation. And in fact, this problem involves, in a hidden way, some algebraic geometry, because of you have to find, to connect curves with some function to generate them, waveforms. Okay, so let's see. So these are the equations, and eventually x prime, y prime will be the curves people observe, people write down or mark on the piece of paper. So first of all, I claim that the size depends on the aberration length. You can see it from here. Larger aberration will mean larger curves. That's what we saw already from the clinic. Second is a very interesting observation. Suppose that the aberration is a homogeneous polynomial. For example, if it is a shape, let's say A30x3 plus A21x squared y plus A12xy squared plus A03y cubed. This is a homogeneous polynomial of degree 3. And I can talk about similar polynomial of degree 4, 5, 6, etc. Suppose it's homogeneous polynomial of degree p. In that case, I claim that the starbursts are going to be at most 2p minus 4 straight line that contain the origin. And if p is odd, the line emanates from the origin. If p is even, it goes through the origin. This is a very simple consequence of this equation for the. But if you substitute the homogeneous polynomial for psi in the first equation, then you simply get, for example, it's fourth order polynomial, you get here an equation of order 4. It's homogeneous for the curves. Therefore, there are lines that pass through the origin, and eventually they're mapped into other lines in the retina. Here is the proof. So you simply substitute into psi the homogeneous polynomial. Then you get a polynomial equation of degree 2p minus 4. The solutions are curves, and therefore there are at most 4 solutions. If p is 4, there are at most 4 solutions. P is 3, at most 2 solutions, which are the roots of this polynomial equation. And you can even tell whether, depending on this, on the order, even or odd, you can tell whether the line will start from the origin or will pass through the origin. Here are some, I don't care about this part. Here are some examples. This is the case when the aberration function is third order cubic, and indeed, you see here 2 starbursts. P equals 3, 2p minus 4 is 3, 2 starbursts passing, starting from the origin. This is the case, this is the fourth order, but I also added a spherical correction. So it depends on alpha. It could be either a disk or such a shape. This is an interesting picture. Now it's a fourth order polynomial, homogeneous, plus a correction, quadratic, from an incorrect prescription. So when beta equals 0, you should see here 4 lines passing through the origin, as the theorem predicts. This is a numerical computation from this function psi. When beta is non-zero, here and here, you see a more interesting shape. This is why, if you remove your glasses, so now beta is non-zero, there is a non-trivial quadratic part, you see some funny shape when you look at a far object at night, under night conditions. I'm just saying here that it's very nice if you can explain what is observed, but the good theory should predict something. So we predicted some features of starburst, which I wrote down here, and then we asked our friend in the clinic to try this. to see if it works. It worked. So this is kind of, it's by Popper's rule, it reinforces the theory. It could predict some new effects of starburst vision. Okay, can you do something more directly? Now, the trouble is it's very, very hard to measure your high order aberration. As I said, it's a requirement for another talk. Ophthalmologists didn't bother about it until about 25 years ago when they introduced LASIK surgery, the refractive surgery. Then they had to measure it because the surgery created high order aberrations. The way they do it is, in my opinion, highly, let's say, unsatisfactory, not to say incorrect, but that's what they do. So it's hard to measure it, but let's say somehow we can measure it. So we asked Norberto Lopez, our friend, our Spanish colleague, to somehow measure his aberrations and also draw what he sees, his starburst. And this is what he drew. Now he is a scientist, so he drew every little shape that he could see, he drew them very, very carefully. Let's look at this. Sorry. Do I go up? Thank you very much. If I look, this is more or less the shape that I predicted based on his measured aberrations. What he should have seen in starburst. This is what he actually saw. They're similar, not exactly the same. I attribute it to the fact that his measured high order aberrations, in my opinion, are spooky. I mean, I don't trust the way they measure high order aberrations. And therefore, we did it artificially. So we took a function psi that we wrote down a formula for it. It includes some fourth order term and some quadratic terms in the aberration function. And for this function, I predicted this shape, the theory I showed you before. Norberto, in the lab, created this phase function and actually measured the shape of the focus on the screen. You can see essentially the same figure. It's the same figure. So this, again, is another support to the theory for starburst. Now, you saw, yes, also it's a funny, very fine shape. I claim this fine shape is due to the internal structure of the caustic. Look at the caustic line. This is the caustic line. But there are also some fine structure. And when Roberto was very careful to draw everything he sees, he also drew this fine structure. Okay, now toward the end of my talk, starbursts are used by countries as symbols. Here is one of them. There's another one of them, Star of David. It's a star, right? And here is the beginning of the American anthem. The American anthem, I won't sing it to you because the melody is impossible to sing, definitely for me. But look at what he says. At the twilight, last gleaming at night, they saw stripes and bright stars through the perilous fight. They saw the star, they saw the starburst, and the guy there wrote down a poem, now the American anthem, based on the starburst that you observe. Conclusion. So first of all, in designing a multifocal spectacles, you require sophisticated mathematics. Visual starbursts are the result of high-order aberrations. They're stable for any individual eye, and you can predict what they see. Can they be used as a clinical tool for ophthalmologists? This last question is not for you, it's for my audience, which is for ophthalmologists. Can you really use them? I believe the answer is yes, because they tell you something about the internal structure of the eye, how the eye, these aberrations are a consequence of the shape of the cornea and the eye lens. So it's a way, kind of a new imaging way, very cheap by the way, extremely cheap to make this test. But maybe I go back. One interesting question that I'm trying to work now is the inverse problem. Suppose I'm giving you the shape of the starburst in a sterile way. Can you find the aberration function psi? I showed from psi how to compute this curve very easily mathematically. Can you do it the other way around? This is a much harder problem, even in sterile form. Forget the fact that what a person writes down includes also the mind, the brain, the visual cortex, just in a sterile way. This turned out to be not an easy problem. In fact, it's an inverse problem, and there's no unique solution. That's easy to show. There's no unique solution. The same shape can be derived from different aberration function psi. But let's say I say, okay, but I know it's fourth order. Then it's almost unique. But the computation is not easy. The inverse problem mathematically is much harder. So I did what lazy mathematicians do these days. I wrote down a machine learning code to do this. I wrote down what they call deep neural networks. I trained the network in the forward direction, gave the many aberration functions. Here are the starbursts. As the network, here are the starbursts, give me the aberration function. This is a lazy way to solve a difficult mathematical problem. And for comma, it worked. For fourth order, not quite, but I'm still working on it. So, and I'm not an expert on machine learning, so I'm trying to do my best here. But it's a very interesting problem. In fact, it's a problem really in algebraic geometry. Because there are many other shapes. I only discussed the case of homogeneous polynomials. In other cases, they're more complicated shape. Can you get from the shape to the aberration function? It's not easy. Okay, now I can go on. There are some other topics where mathematician can be used for example, measuring aberration. It requires some highly non-trivial mathematics, but I won't talk about it today. What else? That's one of my favorite subjects. In developing countries, the major cause for blindness is cataract. No more diseases; they're eradicated. The second cause, people don't have access to glasses, to spectacles, because it's functional blindness. So what we do as a solution that my colleague Sergio Barbero from Madrid and I propose, and also other people, is to develop adjustable spectacles. Spectacles, let's say, consisting of two lenses on each side, and they can move by screw. They can move like this. It turns out you can design them in such a way that by slightly rotating the screw, changing the relative position, you change the optical power. So the idea is to give them for free, people in such countries. Every person will adjust it slightly to himself, till he sees well. This project was stopped halfway. Why? I won't tell you why, many reasons, but it's still, in my opinion, a very interesting project that we didn't complete it. We had nice design, but didn't complete it for different reasons. Finally, another problem where mathematicians should do some work is glaucoma. Now, glaucoma is caused when there's buildup of pressure in the eye fluid. And why there's buildup of pressure? Because the fluid in the eye is drained through a porous medium called trabecular network. And this gets blocked, like a sponge. It gets blocked with time, and then fluid cannot go through, so pressure builds up. There is medicine for this, doesn't always work. Or people sometimes they install a small needle with a small, very narrow cylinder to drain the fluid in the eye, or other method. But I believe that to solve the problem, really, you must study the mechanical properties of this network mathematically, and find ways to improve the permeability of this network. But that's not optics. This is fluid mechanics. Okay, I stop here. Thank you very much.
Questions?
If I understood well, all your theory treats light as being monochromatic, isn't it?
What?
Monochromatic, a single frequency. Refraction, as far as I understand, depends
on the wavelengths, you mean?
Pardon me?
Wavelength dependence of the light?
Yeah.
Yes,
So I didn't see any mention
of course.
of that.
I didn't discuss it because we ignore it. But you're right, it's so-called chromatic aberration of the lens. It is determined by the so-called Abbe number of the spectacle. If you buy high quality lenses, high quality material, the Abbe number, they will be very small, very minor. So if you buy a lens, they say to cheap lens, cheap multifocal lens, big or very thin lens, because the refraction index is very high. Be careful, because it might have a large Abbe number and create chromatic aberration. It's called chromatic aberration. This can't be
The number.
Abbe. Oh, Abbe. Oh, Abbe. Abbe was Abbe was the extremely important guy. He worked in the University of Vienna in Germany. He designed the best microscope in the 19th century. Why very important? Because he gave them to Koch, and Koch used them to find the germs for cholera, TB, and many other diseases. So he revolutionized microscopy, Abbe. And this number quantifies the chromatic aberration, how much the lens refraction property depend on the wavelengths.
So you want this number to be small.
I think so. I don't remember the definition because I don't use this stuff, but I think it should be small, or at least near 1 or something. I don't remember. But this controls. So you design it in the yellow. All the designs are in the yellow. But if you go deep to the red or the blue, you may get chromatic aberration. In my design, I ignore them. Some people claim to put them in the design in the weight function, to put several different wavelengths in the weight function. In contact lens design, we tried to do it, but we didn't see a major effect on the final outcome. But certainly a good point.
Not. We'll have some coffee.
Very important.
Yeah. O café que não tinha era uma mesa de botar.
So could you follow something? Nice pictures, no?
Nice.
Oh, it's a nice picture. Also a movie. You're from the mathematics department?
Computer science.
Ah.
I'm a mathematician.
No, but the question you asked me typical to optics researchers. They always.
Well, the term chromatic aberration, something I know, but I think telescopes, they.
Okay, thank you very much. Thank you very much. Okay.
So,